On May 10th, 2024, something arrived at Earth that shouldn't have been possible. Not the storm itself. Solar storms happen. They've happened for as long as the sun has existed. What arrived was something quieter, something the instruments weren't designed to notice. In the days following the event, scientists began comparing measurements. Aurora appeared at latitudes where they hadn't been seen in decades. Power grids fluctuated in ways that didn't match the storm's official severity rating. Satellite operators reported anomalies that fell just outside standard monitoring parameters. Nothing catastrophic. Nothing that made headlines for more than a few days. But in the weeks that followed, a pattern emerged in the data. Not in what the storm did to Earth's magnetic field, but in what Earth's magnetic field had already become before the storm arrived. The readings weren't wrong. The models weren't broken. The problem was simpler and far more unsettling. We'd been measuring protection, but we hadn't been measuring change. If you're here because you value thoughtful exploration of cosmic events that reshape our understanding of Earth's place in space, or because late-night science storytelling helps you see the universe more clearly, this channel exists for exactly that purpose. Like and subscribe if this approach resonates with you. Enable notifications if you'd like to be part of future investigations into phenomena that don't fit easily into existing explanations. No pressure. Only if it genuinely adds value to how you experience science. You don't usually hear about solar storms in the past tense. They're forecast events, predicted arrivals. Space weather agencies track coronal mass ejections from the moment they leave the sun's surface, calculating trajectories, estimating impact windows, issuing alerts to satellite operators and power grid managers days in advance. The May 2024 event followed this pattern, almost perfectly. On May 8th, solar observatories detected a series of X-class flares erupting from sunspot region AR 3664, one of the largest and most complex active regions observed in years. The eruptions were violent enough to be visible in multiple wavelengths simultaneously. Plasma clouds began racing outward at speeds exceeding 1,000 kilometers per second. Models calculated arrival times, predictions were issued, the world prepared for a significant geomagnetic storm, and on May 10th, it arrived. But here's what didn't fit. The storm's official classification, a G5, the highest level on the geomagnetic storm scale, was based on measurements taken at Earth's surface and in near-Earth space. These measurements record disturbances in the planet's magnetic field, how much it compresses, how deeply solar particles penetrate, how dramatically the field lines oscillate under pressure. By those standards, the May 2024 storm was extraordinary, the kind of event that occurs perhaps once or twice per solar cycle. Yet when researchers began comparing this storm to historical events of similar magnitude, something felt wrong. Not the data itself. The measurements were clear. Aurora stretched across Europe, Asia, and North America, visible as far south as the Caribbean and Northern Africa. Radio blackouts disrupted communications. GPS systems experienced localized interference. These were all expected consequences of a G5-level disturbance. What felt wrong was the proportionality. The solar wind conditions that struck Earth's magnetosphere, the density of particles, their velocity, the strength and orientation of the embedded magnetic field should have produced a strong storm, perhaps even a severe one. But a G5? The most extreme classification? Historical records suggested that similar upstream solar wind conditions had, in the past, produced notably less dramatic surface effects. The difference wasn't in what arrived from the sun, it was in how Earth responded. This is where the story shifts from astronomy to something more unsettling. Because if the incoming solar wind hadn't changed, if the sun's behaviour was well within historical norms, then the variable in the equation wasn't external. It was us. Or more precisely, it was the magnetic field that has protected this planet for hundreds of millions of years, and the fact that it no longer responds to solar storms the way it used to. Scientists don't speak openly about magnetic field weakening in the context of individual storm events. It's considered mixing timescales, comparing phenomena that operate on vastly different temporal scales. Solar storms last days, magnetic field evolution unfolds over centuries and millennia. But May 2024 did something unusual. It created a situation where both timescales became visible in the same data set. The storm itself was a probe, an unintentional experiment. It delivered a controlled input, specific amount of energy and particle flux to Earth's magnetic environment, and the response it triggered was stronger, more geographically widespread, and more deeply penetrating than the input alone could explain. Which meant that Earth's magnetic defences had changed in ways that weren't fully captured by existing monitoring systems. This wasn't a failure of measurement. Every instrument performed exactly as designed. Magnetometers recorded field strength, satellites tracked particle populations, ground-based observatories monitored ionospheric currents. All the data was correct. What wasn't correct was the assumption that Earth's magnetic field in 2024 functions identically to Earth's magnetic field in 1989 or 1959 or 1859, because it doesn't. And the May superstorm didn't reveal this through catastrophic failure or unprecedented damage. It revealed it through subtle asymmetry, through aurora, appearing in unexpected locations, through field distortions that didn't match predictive models, through a quiet mismatch between cause and effect that only became visible when researchers looked closely at what the storm had actually done versus what it should have done. The disturbing part isn't that Earth's magnetic field is changing. We've known that for decades. The disturbing part is that we're only now beginning to understand how those changes translate into real-world vulnerability during actual solar storm events, and that our detection systems weren't designed to measure the thing that turned out to matter most. Not the strength of the storm arriving, but the strength of the protection that's no longer there. There's a specific kind of confidence that comes from long-term measurement. When you have instruments that have been recording the same phenomenon for decades, sometimes over a century, patterns emerge. Baselines become established. You learn what normal looks like. You develop the ability to recognize anomalies the moment they appear in the data. This is the foundation of geomagnetic monitoring. Observatories scattered across the planet have been tracking variations in Earth's magnetic field since the 1830s. Some stations have nearly continuous records spanning more than 180 years. The data they've collected forms one of the longest-running geophysical datasets in existence, and it's extraordinarily precise. Modern magnetometers can detect changes in field strength smaller than 1 part in 100,000. They record variations occurring over timescales ranging from fractions of a second to decades. They operate continuously in all weather conditions, generating datasets so detailed that researchers can reconstruct the exact behavior of Earth's magnetic field during every major solar storm in the instrumental record. This is what made the May 2024 analysis possible. Scientists could compare the storm's magnetic signature to events from 1989, 1972, 1921, even the great 1859 Carrington event, using both direct measurements and reconstructed estimates. They could quantify disturbance levels with extraordinary precision. But precision and completeness are not the same thing, because geomagnetic observatories measure only what happens at Earth's surface. They record the magnetic field's behavior at fixed points on the ground. They capture variations in intensity and direction as the field responds to external forcing from solar wind and internal dynamics in Earth's core. What they don't measure, what they were never designed to measure, is the three-dimensional structure of the magnetosphere itself. The magnetosphere is not a simple bubble. It's a dynamic, asymmetric cavity carved out of the solar wind by Earth's magnetic field, extending tens of thousands of kilometers into space on the day side and stretching into a long tail on the night side that reaches well beyond the moon's orbit. Its shape changes constantly. It compresses under solar wind pressure. It develops instabilities. Plasma populations move through it in complex patterns driven by magnetic reconnection and particle acceleration processes. And critically, its overall size and structural integrity depend directly on the strength of Earth's internal magnetic field. A stronger planetary field creates a larger, more robust magnetosphere. A weaker field results in a smaller cavity, one that offers less shielding and allows solar particles to penetrate closer to Earth's surface. This matters because what ground-based magnetometers record is the end result, the surface expression of magnetospheric dynamics. They see the disturbance after it has already propagated through the entire system and reached the ground. They don't see the magnetosphere failing to deflect particles that it would have deflected 20 years ago. They don't see the boundary layer eroding inward. They don't see the structural thinning that allows solar wind to couple more efficiently to the inner magnetosphere. What they see is an enhanced disturbance at the surface, a stronger geomagnetic storm index, aurora at lower latitudes, and if you only look at surface measurements, you might conclude the sun delivered a more powerful blow, but that's not necessarily what happened. In the weeks following May 2024, a small number of research groups began examining satellite data from NASA's Magnetospheric Multiscale MMS mission and the European Space Agency's Swarm constellation. These spacecraft don't sit on the ground. They orbit through different regions of near-Earth space, measuring magnetic field strength and plasma conditions in 3 dimensions. What they found was subtle, not dramatic, not the kind of result that generates headlines. The magnetopause, the outer boundary where Earth's magnetic field meets the solar wind, had been compressed closer to Earth than models predicted given the measured solar wind conditions. Not catastrophically closer, just closer, a few hundred kilometers, maybe 1,000 in some locations. That doesn't sound significant. In a structure extending 60,000 kilometers sunward, a shift of 1,000 kilometers seems marginal. But magnetospheric physics doesn't scale linearly. When the magnetopause compresses inward, it doesn't just move, it changes the geometry of the entire system. Magnetic field lines that previously closed far from Earth now close closer in. Reconnection sites shift, particle entry pathways alter. The efficiency with which solar wind energy couples into the magnetosphere increases. Small changes in position translate into measurable changes in how the system responds to forcing. And here's the part that existing ground-based monitoring can't capture. If Earth's internal field strength has decreased by even 5 to 10% over the past several decades, a change well within the observed trend, the magnetopause equilibrium position shifts inward proportionally, not during storms, all the time, as the new baseline. Ground magnetometers don't measure this. They measure deviations from whatever the current baseline happens to be. They're differential instruments designed to detect changes, not absolute structural configuration. which means they can correctly record that a storm in 2024 produced surface disturbances equivalent to a G5 classification, while remaining completely blind to the fact that the same solar wind conditions would have produced a G4 or even G3 response in 1990. The storm index goes up, the official severity increases, but the interpretation that the sun delivered a more powerful event may be fundamentally wrong. It's not that the measurements are inaccurate, it's that they're measuring the consequence, not the cause. And in a system where the protective structure itself is slowly changing, measuring only the consequences creates a deepening blind spot, one that makes every storm look slightly more severe than it would have been before, without ever revealing why. This is what made 2024 exposed, not through instrument failure, not through missed predictions, through the quiet realization that our most trusted, most precise, longest-running datasets might be telling us exactly what's happening at Earth's surface, while remaining silent about the structural changes happening in the space above us. Changes that determine how vulnerable we actually are, and changes that won't appear in any ground-based record until they've already progressed far enough to matter. When people talk about the worst solar storm in recorded history, they mean September 1st, 1859, the Carrington event, named after British astronomer Richard Carrington, who observed the solar flare that triggered it. A white light flare so intense it was visible to the naked eye through his telescope's projection. Within hours, a massive coronal mass ejection struck Earth's magnetosphere with enough force to generate aurora, visible in the Caribbean, Hawaii, and across equatorial regions where such phenomena had never been documented. Telegraph systems across Europe and North America failed. Operators reported sparks leaping from equipment. Some lines continued functioning even after being disconnected from their batteries, powered entirely by electrical currents induced in the wires by the geomagnetic disturbance. It remains the benchmark, the reference event, the storm every modern assessment of space weather risk uses as the worst-case scenario. But it wasn't the only one, and it may not even have been the worst. In 2012, a team of researchers analysing ice core data from Greenland identified a spike in nitrate deposition, a chemical signature left behind when high-energy solar particles interact with Earth's upper atmosphere. The spike dated to approximately 1770, plus or minus a few years. The signal was strong, stronger in fact than the signature left by the Carrington event itself. This caught attention, but not widespread concern. Ice core records have limited temporal resolution. The dating methods involve uncertainties. A single chemical spike, even a large one, doesn't tell you much about what actually happened at Earth's surface during the event. So the finding remained a footnote, an interesting anomaly in the paleoclimate record, nothing more, until researchers started looking at something else entirely. Historical archives, not scientific records, not astronomical observations, just documents, letters, ship logs, newspaper accounts, the scattered written record of daily life in the 18th century. And in those documents, buried in the routine documentation of a pre-industrial world, they found descriptions, December 1770. Reports from observers across Europe and Asia describing brilliant aurora displays. Red, green, and white curtains of light extending across the entire visible sky. Accounts from as far south as Timor and the Philippines mentioning strange lights and red glow covering the heavens. A Spanish missionary in the Philippines wrote that the night sky had turned the colour of blood, bright enough to read by, lasting for several hours. In Japan, historical records documented what observers called red vapour filling the sky on multiple nights in late 1770. Similar accounts appeared in Korean royal court records, Chinese provincial archives, Russian monastery logs. None of these observers knew what they were seeing. Aurora weren't understood in 1770. They were interpreted as omens, atmospheric fires, reflections of distant volcanic eruptions, anything except what they actually were. But the geographic distribution was unmistakable. Aurora at tropical latitudes, sustained multi-night displays, descriptions matching the phenomenology of extreme geomagnetic storms, and yet no corresponding technological disruption. Because in 1770, there was no technology to disrupt. No telegraph systems, no power grids, no satellites, no infrastructure vulnerable to geomagnetically induced currents. The storm happened, it was observed, it was documented in fragmentary, non-scientific language across multiple continents, and then it was forgotten, because without technological consequences, it didn't matter. It was just strange lights in the sky. Beautiful, perhaps, unsettling to some, but not consequential in any way that would cause the event to be preserved in collective memory or scientific literature. Here's what makes this uncomfortable. If the 1770 event was comparable to, or larger than, the Carrington event in terms of geomagnetic disturbance, then our worst-case scenario isn't actually worst case. It's just the worst case that happened to occur after we developed technology sensitive enough to fail when struck. The Carrington event damaged telegraph systems, yes, but telegraph systems in 1859 were limited networks, small-scale infrastructure, operated manually by individuals who could shut down equipment when problems arose. A Carrington-level storm today would interact with a fundamentally different technological landscape. Continental-scale power grids, autonomous satellite constellations, GPS-dependent navigation and timing systems, communication networks with no manual override. This is widely understood. It's why space weather risk assessment exists. But risk assessment based on the Carrington event assumes that 1859 represents the upper bound of what's physically possible during a solar maximum. The 1770 data suggests otherwise. It suggests that storms significantly more severe than Carrington can and do occur, and that we only know about 1859 because it happened to hit us after we'd built something fragile enough to notice. Now consider the next part. The 1770 storm occurred during a solar maximum, so did Carrington. Both events fit comfortably within the expected pattern of solar activity. The sun becomes more active every 11 years, peak activity produces the most energetic eruptions, and occasionally those eruptions are directed at Earth. But when researchers extended the ice core analysis further back in time, they found additional nitrate spikes, events separated by periods much longer than 11 years, some occurring during what should have been solar minimum conditions, periods when the sun is supposed to be relatively quiet. One event, tentatively dated to around 660 BCE, showed a nitrate spike larger than anything in the subsequent 500-year record. No written accounts exist from that era. No way to know what observers might have seen. No way to reconstruct what happened at Earth's surface. Just a chemical signature in Greenland ice, indicating that something arrived from the sun, or possibly from elsewhere in the galaxy, and interacted with Earth's atmosphere with enough energy to leave a mark still detectable 2,600 years later. These findings don't overturn existing models of solar activity. The 11-year cycle is real. Solar maxima do produce more frequent and more energetic eruptions. But what the ice cores reveal is that the sun is capable of events that don't fit neatly into the cyclical pattern we've observed over the past 400 years of telescopic astronomy. Rare events, separated by centuries, perhaps millennia. Events that leave no historical memory because they occurred before written records, or because they struck a pre-industrial world where their consequences were invisible. And this brings us back to May 2024. The storm wasn't Carrington scale. It wasn't even close to what the 1770 event may have been. By any reasonable measure, it was a strong but manageable geomagnetic disturbance. Yet it produced surface effects, aurora distributions, communication disruptions, grid fluctuations, that seem disproportionate to the solar wind conditions that caused them. If our baseline for severe space weather is calibrated against the Carrington event, and if Carrington itself may not represent the true upper limit of solar activity, then we're left with two compounding uncertainties. First, we don't actually know how bad solar storms can get. Second, we don't know how Earth's changing magnetic field will respond. When a truly extreme event, something on the scale of 1770 or worse, eventually arrives, the forgotten storms of the past aren't forgotten because they were unimportant. They're forgotten because they struck a world that had nothing to lose. We are no longer that world. If you look at diagrams of Earth's magnetic field in textbooks, you see something elegant. Clean, symmetrical field lines arcing from pole to pole. A structure that looks almost geometric. The kind of pattern you'd get if you placed a bar magnet inside a sphere and mapped the resulting field configuration. This is called a dipole field. And for most practical purposes, it's a reasonable approximation of how Earth's magnetism actually works, except it's becoming less reasonable every year. Earth's magnetic field isn't generated by a bar magnet. It's generated by convective motion of molten iron in the planet's outer core. A churning, electrically conductive fluid layer roughly 2,000 kilometers thick, rotating with the planet, driven by heat escaping from the solid inner core below. This process, called the geodynamo, produces a magnetic field through electromagnetic induction. The moving fluid generates electric currents, which in turn generate magnetic fields, which influence the fluid motion, creating a self-sustaining feedback loop that has operated for billions of years. Under stable conditions, this system naturally organizes itself into a predominantly dipolar configuration. The field emerges from the core with most of its energy concentrated in a north-south orientation, aligned roughly with Earth's rotation axis. But the geodynamo isn't a simple machine. It's a chaotic, turbulent system, and while the overall field structure tends toward dipole symmetry, it's never perfectly dipolar. There are always deviations, asymmetries, localized distortions where the field strength differs from what a perfect dipole would predict. These deviations are called non-dipole components. For most of recorded history, they've been small. Measurable? Yes. Scientifically interesting, certainly. But small enough that treating Earth's field as primarily dipolar remained accurate for navigation, for understanding magnetospheric dynamics, for calculating how the planet interacts with the solar wind. That's changing. Satellite measurements from the past 2 decades, particularly data from the European Space Agency's SWARM mission, have revealed that the non-dipole components of Earth's field are growing. Not uniformly, not everywhere. But in specific regions, the magnetic field structure is deviating further and further from the clean dipolar pattern that dominated for centuries. And the most pronounced deviation is occurring in a region that was already anomalous to begin with, the South Atlantic anomaly. We'll examine that region in detail shortly. But first, it's important to understand what it means when the dipole weakens and non-dipole components grow. Imagine the magnetic field as a composite structure, a strong central framework, the dipole, providing most of the overall strength and shape, with smaller contributions from more complex geometries layered on top. As long as the dipole dominates, the system behaves predictably. The magnetosphere maintains a consistent size and shape. Solar-wind interactions follow well-understood patterns. Particle entry pathways remain stable. But if the dipole begins to weaken while non-dipole components remain constant, or even strengthen, the field's geometry shifts. It doesn't collapse, it doesn't disappear, it just becomes different, more complex, less symmetric, harder to characterize with simple models, and this is exactly what's happening. Global measurements show that the dipole moment, the quantity that describes the strength of the field's dipole component, has decreased by approximately 9% over the past 180 years. 9% might not sound dramatic. It's a slow change, gradual, the kind of thing that unfolds over multiple human lifetimes. But the rate of change isn't constant. In the past 2 decades alone, the dipole moment has decreased by roughly 3.5%. That's more than 1/3 of the total decline occurring in less than 1/10 of the time. The weakening is accelerating. Meanwhile, certain non-dipole components have been intensifying. The quadrupole and octupoly terms, higher-order mathematical descriptions of field geometry, have been growing stronger in specific regions, particularly in the southern hemisphere. This creates a situation where the field's total energy is declining, but the spatial distribution of that energy is becoming more uneven. Some regions experience greater weakening than the global average. Other regions show relative strengthening, not because the field is actually getting stronger there, but because the redistribution of energy concentrates more of the remaining field into localized structures. From the ground, this is nearly invisible. A 9% decrease in dipole strength translates to a barely perceptible change in compass behavior. Navigation still works. Magnetic surveys still function. The field is still strong enough to deflect solar wind and protect the atmosphere from erosion, but from space, the consequences are more immediate. Satellite operators have known for years that low Earth orbit spacecraft experience higher radiation doses when passing through certain regions. The South Atlantic anomaly in particular requires special operational procedures. Instruments are sometimes shut down during transits, data collection is paused, sensitive electronics are placed in safe mode. These procedures were developed based on radiation maps compiled over decades of satellite operations. But those maps are aging, because the anomaly isn't static. It's drifting westward at roughly 20 kilometers per year, and it's expanding. The region of reduced field strength now covers a larger geographic area than it did when the first radiation maps were created. More importantly, it's deepening. Field strength within the anomaly's core has continued to decline, even as the global dipole weakens, which means the gap between the anomaly and surrounding regions is widening. This has practical implications. Satellites that were designed with shielding adequate for radiation levels measured in the 1990s are now operating in an environment where peak radiation exposure has increased by measurable amounts. Not enough to cause immediate failures, but enough to shorten operational lifespans, enough to increase error rates in memory systems, enough that engineers designing new satellites must account for radiation environments that didn't exist when the previous generation of spacecraft was built. And all of this stems from the same underlying process. The dipole is weakening, and the field's geometry is reorganizing into something more complex. Here's why this matters for understanding May 2024. When a solar storm strikes Earth, the magnetosphere's response depends on its structure. A strong, symmetric dipole field creates a large, stable magnetosphere with well-defined boundaries and predictable dynamics. A weakening dipole with growing non-dipole components creates something messier. Boundaries become less distinct. Asymmetries in field strength translate into asymmetries in how different regions of the magnetosphere respond to the same external forcing. The southern hemisphere, where non-dipole components are strongest, becomes more vulnerable to particle penetration than the northern hemisphere, and the models we use to predict storm impacts, models calibrated against decades of observations made when the dipole was stronger and the field was more symmetric, begin to underestimate actual disturbance levels, not drastically, not in ways that invalidate the models entirely, just slightly, consistently, in directions that make storms appear more severe than the incoming solar wind alone would suggest. This is what researchers started noticing in the May 2024 data. Aurora appeared at lower latitudes in the southern hemisphere than in the northern hemisphere, despite similar geomagnetic latitude. Field disturbances were asymmetric in ways that didn't match predictions based on solar wind orientation. Small discrepancies, but persistent, and concentrated in regions where the dipole is weakest and non-dipole components are strongest. The storm revealed what steady-state measurements had been showing for years. Earth's magnetic field is transitioning from a configuration dominated by simple dipolar geometry to something more complex. And we don't yet know what that means for how the planet will respond when the next truly large solar storm arrives. Because all of our worst-case models assume the field looks like it did in 1859. It doesn't, and it's moving further from that configuration every year. There's a place above the South Atlantic Ocean where space comes closer to Earth than it should. Not physically, the atmosphere doesn't thin there. Orbital altitudes don't change. But the protective boundary between Earth's surface and the radiation environment of space, the invisible barrier maintained by the planet's magnetic field, dips inward, weakens, allows charged particles from the inner Van Allen radiation belt to descend hundreds of kilometers lower than they can anywhere else on the planet. This region is called the South Atlantic Anomaly. It's been known since the 1950s, when the first satellites began experiencing unexplained malfunctions while passing over the South Atlantic. Instruments would glitch, star trackers would report impossible readings, computer memory would flip bits, individual zeros changing to ones or ones to zeros, corrupting data for no apparent mechanical reason. It took several years to understand what was happening. The satellites weren't malfunctioning, they were being hit by radiation. High-energy protons trapped in Earth's magnetic field, ordinarily confined to altitudes well above typical satellite orbits, were reaching down into the region where spacecraft operated. The reason was simple. Earth's magnetic field isn't centered on the planet's geographic center. The geodynamo operates in the outer core, roughly 3,000 kilometers below the surface. But the field it generates doesn't emerge symmetrically. The magnetic axis is tilted relative to the rotation axis, and more importantly, the center of the dipole field is offset from Earth's physical center by several hundred kilometers. This offset is small in absolute terms, but in a structure extending tens of thousands of kilometers into space, small displacements at the source translate into large variations in field strength at altitude. Over the South Atlantic, the offset causes the magnetic field lines to sit lower relative to Earth's surface. The result is a region where the inner Van Allen belt, a torus of trapped radiation encircling the planet, comes closer to the ground than anywhere else. For decades, this was treated as a curiosity, an operational nuisance for satellite engineers, but nothing more. Spacecraft were designed with additional shielding. Mission planners routed satellites to minimize time spent in the anomaly. The International Space Station's crew schedule was adjusted so astronauts slept in more heavily shielded modules during overhead passes. The anomaly was understood, managed, accounted for, but it wasn't static. In 1990, the South Atlantic anomaly covered roughly 8 million square kilometers, an area about the size of Brazil. By 2020, it had expanded to more than 15 million square kilometers. The boundary of reduced field strength had pushed northward, westward, and southward. What was once a localized region centered over the South Atlantic now extended across significant portions of South America, reaching from southern Brazil nearly to the southern tip of Argentina and westward over the Pacific. More concerning than the expansion was